Imagine you have a ball and you have a hill. You roll the ball towards the hill. If you give it a gentle push, it will roll partway up and then roll back down. That makes sense. It doesn't have enough energy to get to the top. If you give it a really hard push, it will roll all the way up and over to the other side. That also makes sense. It has enough energy to overcome the obstacle, the barrier of the hill. Now, what if I told you that you could give the ball a gentle push, just enough to get it a third of the way up the hill, and then, a moment later, you might find it on the other side? It never went over the top. It didn't roll around the hill, it just sort of vanished from one side and reappeared on the other. You would quite reasonably say that's impossible, it defies logic, it breaks the rules of how the world works. A solid ball cannot pass through a solid hill, and you would be right for our world. For the world of baseballs and mountains and people and cars, but at the smallest scales of reality, the world of electrons and protons and other fundamental particles, this impossible thing happens all the time. It has a name. It's called quantum tunneling, and it doesn't just defy our everyday logic, it forces us to reconsider what logic even means when it comes to the fabric of existence. To understand why tunneling feels so wrong, we first have to appreciate the rules it seems to break. Our entire intuition about the universe is built on what we can see and touch. We call this classical physics. It's the physics of Isaac Newton. It's a world of cause and effect, a world of solid objects with definite locations and definite speeds. If you know where something is and how fast it's moving, you can predict its entire future path. It's a clockwork universe. In this classical world, energy is king. Energy is the currency you need to do things. To lift a box, you need energy. To climb a hill, you need energy. An energy barrier is exactly what it sounds like, a wall of energy you have to be tall enough or powerful enough to get over. The hill is an energy barrier for the ball. The ball's kinetic energy, its energy of motion, has to be greater than the potential energy of the hill's peak. If it's not, the ball fails. Every single time. There are no second chances, no lucky breaks. The math is absolute. The ball cannot be in a place where it doesn't have the energy to be. A bank account with $10 cannot spend $100. That is the logic of our world. This logic extends to everything. A person can't walk through a wall because the atoms in their body don't have enough energy to push apart the atoms in the wall. The wall represents an immense energy barrier. It's solid. We are solid. That solidity feels like a fundamental truth of reality. Things occupy their own space. They don't magically appear in other spaces. To get from point A to point B, you have to travel the path between A and B. You can't just skip the journey. For centuries, this was our picture of the universe. It was predictable, reliable, and logical. It worked perfectly for calculating the orbits of planets, the firing of cannons, and the building of bridges. But then, as we started to probe the very, very small, we found that this neat and tidy clockwork universe began to fall apart. The rules that govern planets and baseballs simply did not apply to the atoms they were made of. A new set of rules was needed. That new set of rules is called quantum mechanics. And it's where logic takes a very strange turn. The single most important concept to grasp, the one that unlocks the secret of tunneling, is that things in the quantum world are not what they seem. An electron, for example, is not just a tiny solid ball. Sometimes it acts like a particle, a little point of stuff. But other times, it acts like a wave. Think about a wave in a pond. It's not in one single place. It's spread out, it has peaks and troughs. It's a disturbance, a vibration spread across a region. A quantum particle is like that. It's not a dot located at a precise coordinate. It's more like a cloud of possibility. This cloud is described by something called a wave function. The wave function doesn't tell you where the particle is. It tells you the probability of finding the particle at any given place if you were to look for it. Where the wave is high, there's a high chance of finding the particle. Where the wave is low, there's a low chance. But until you look, it's not really in any one place. It is the wave. It is the cloud of all possibilities at once. This is the first major break with our logic. We are used to things being somewhere. My keys are on the table. The car is in the driveway. A quantum particle is different. Its existence is probabilistic, smeared out over space according to its wave function. Mental shift from certainty to probability. The universe, at its core, isn't a clockwork machine. It's a casino. Now let's go back to our hill. But instead of a ball, let's send a quantum particle, like an electron, towards it. The hill is still an energy barrier. The electron doesn't have enough energy to get over the top. In the classical world, the story would end here. The electron would hit the barrier and bounce back. As this wave hits the energy barrier, something interesting happens. The wave doesn't just stop dead. A large part of it is reflected, just like a water wave hitting a wall, but a little piece of the wave actually penetrates into the wall. It goes inside the barrier. Inside the barrier, the wave changes. It starts to decay very, very quickly. It shrinks rapidly, like the sound of a shout dying out as it goes through a thick door. For every bit of distance it travels into the barrier, its height, its amplitude drops off exponentially. This means it fades away incredibly fast. For a thick barrier, the wave will shrink to basically zero before it can get very far. But what if the barrier is very, very thin? What if our hill is more like a thin wall? The wave starts to penetrate it. It decays rapidly. But if the wall is thin enough, the wave might not have decayed all the way to zero by the time it reaches the other side. There might be a tiny little, almost non-existent ripple of the wave that makes it all the way through. And here is the crucial point. The height of the wave function represents the probability of finding the particle. So if there is a tiny non-zero part of the wave on the other side of the barrier, that means there is a tiny non-zero probability of finding the particle there. So you look, you make a measurement. The universe rolls its dice. And most of the time, you'll find the electron back on the original side having been reflected. But sometimes, maybe one time in a million or a billion, you'll look and poof. There it is, on the far side of the barrier. It never had the energy to go over. It didn't break a hole through the barrier. It just appeared on the other side. It has tunneled. This is what quantum tunneling is. It is the consequence of the wave nature of particles. It's not that the particle gathers up some secret energy and leaps over the wall. It's that the particle's existence, its very location, is described by a wave of probability, and that wave can leak through places that should be forbidden. Now, we can really face the question, how does this defy logic? It assaults our intuition on several fronts. First, there's the problem of energy. The whole idea feels like a violation of the conservation of energy. It's like getting something for nothing. You didn't pay the energy toll to get over the hill, but you ended up on the other side anyway. This is probably the biggest conceptual hurdle, but physicists will tell you that energy is still conserved. The particle on the other side has the exact same energy it started with. It didn't gain any. So how did it cross the high energy region in the middle? The quantum answer is that it didn't, not in the way we think. It wasn't in the barrier, traveling through it like a mole. The wave function was in the barrier. The potential for the particle to be there existed, but asking where the particle was during the tunneling process is a question that quantum mechanics says is meaningless. The particle was not at a definite location. It was a wave that was simultaneously on both sides of the barrier. When you made the measurement and found it on the other side, the wave function collapsed and the particle's position became definite. The process itself is not a journey in the classical sense. It's a probabilistic jump. It's like having a bank account with $10 and a store that costs $100 to enter. You can't go in. But in the quantum world, there's a tiny, tiny chance you can just appear inside the store, still with only $10 in your pocket. You didn't pay the entry fee, the rules of probability just let you skip it. Second, there is the problem of locality and causality. We are deeply accustomed to the idea that to get from here to there, you must travel the space in between. Motion is a continuous process. Tunneling seems to suggest that a particle can cease to exist at one point and instantly begin to exist at another, without ever having been in the intervening space. This feels like teleportation. It challenges our very notion of what it means to move. Again, the wave nature of the particle is the key. Since the particle wasn't a tiny point to begin with, it wasn't ever just here. It was a spread out wave of potential. The tunneling event is not a particle traveling, but a wave function evolving. The probability leaks through the barrier, and if the dice land a certain way, a measurement on the other side will find the particle. The Ernie is a mathematical abstraction, not a physical path that could be filmed or tracked. This is profoundly unsettling. It means that at its most fundamental level, reality is not a series of continuous events, but a series of probabilistic jumps. Third, tunneling destroys our comfortable idea of solidity. We think of a wall as an absolute barrier. It's solid, it's there. But quantum mechanics tells us that solidity is just a matter of probability. A wall is just a very, very, very effective energy barrier made of trillions of atoms. For a single particle, it's not an absolute no, it's a probably not. Now, for a large object like a person, the probability of tunneling is so fantastically small that it might as well be zero. A person is made of trillions upon trillions of atoms. For you to tunnel through a wall, every single one of those particles, in perfect coordination, would have to simultaneously tunnel through the wall to the exact same relative positions on the other side. The odds of this happening are smaller than the odds of winning every lottery on Earth every day for the rest of your life. If you waited for the entire age of the universe, you wouldn't see it happen. So our classical experience that people don't walk through walls is safe. The logic holds up on our scale because the probabilities are so extreme. But at the fundamental level, the truth is different. The wall isn't an impenetrable fortress, it's just a place where the probability of finding a particle is astronomically low. Solidity is not an absolute property, it's a statistical certainty. This might all sound like some strange philosophical thought experiment. A quirky feature of a theory that only applies to a subatomic world we can never see. But that couldn't be further from the truth. Quantum tunneling isn't just real, it's one of the most important processes in the universe. Our very existence depends on it. Take the sun. The sun shines because of nuclear fusion happening in its core. The fusion is the process of light atomic nuclei, like hydrogen, smashing together to form heavier nuclei, like helium, releasing a tremendous amount of energy. The core of the sun is incredibly hot and dense, but even there, it's not quite hot enough for fusion to work according to classical physics. The problem is that the nuclei of atoms are positively charged, and like charges repel each other. As two hydrogen nuclei, which are just single protons, get close, a powerful electrostatic force pushes them apart. This force creates an enormous energy barrier, often called the Coulomb barrier. According to classical calculations, the protons in the sun's core are not moving fast enough, they don't have enough energy to overcome this repulsion and get close enough to fuse. If classical physics were the only thing at play, the sun would not ignite, it would just be a big warm ball of gas. But the protons are quantum particles. They have wave functions, and even though they don't have enough energy to go over the Coulomb barrier, they have a small but significant chance to tunnel through it. A proton gets close to another one. Its wave function leaks through the repulsive barrier, and there's a non-zero probability that it will suddenly find itself right next to the other proton, close enough for a different, stronger force, the strong nuclear force, to take over and bind them together. Fusion occurs, energy is released, the sun shines, life on Earth is possible. Every ray of sunlight that warms your face is a direct consequence of a process that your brain tells you is impossible. Trillions of tiny particles are right now passing through walls. They don't have the energy to climb, all so that our star can burn. Quantum tunneling is not a footnote in the story of the universe, it's a headline. And it's not just in stars, the technology that powers our modern world is riddled with quantum tunneling. Take the flash memory in your phone or your computer's solid-state drive SSD. This technology stores information, the 1S and OS of digital data, by trapping electrons in a tiny, isolated chamber called a floating gate. This gate is surrounded by a very thin layer of insulating oxide, which acts as an energy barrier. To write data, a voltage is applied that is strong enough to allow electrons to tunnel through the insulating layer and get trapped in the gate. To erase the data, the voltage is reversed and the electrons tunnel back out. The key is that when the voltage is off, the barrier is too high for the electrons to escape classically. They are trapped. But they are trapped by a quantum fence, not a classical one. The insulating layer has to be engineered to be thin enough for tunneling to be reliable when you want it, but thick enough that electrons don't just leak out on their own over time. The entire digital revolution, the ability to store vast amounts of data on tiny chips, relies on our ability to precisely control this impossible quantum leap. We have even built machines that use tunneling to see the world in a way we never could before. The Scanning Tunneling Microscope STM is a remarkable device that can produce images of individual atoms on a surface. It works by bringing an incredibly sharp metal tip, ideally ending in a single atom, to within a nanometer of the surface you want to scan. That's a billionth of a meter. There is a tiny vacuum gap between the tip and the surface. Classically, no electricity should flow. The air gap is a perfect insulator, a barrier. But if you apply a small voltage, electrons from the surface can tunnel across the forbidden gap to the tip. This creates a tiny electrical current, the tunneling current. This current is extraordinarily sensitive to the distance. If the tip moves closer to the surface by the width of a single atom, the tunneling current increases dramatically. If it moves farther away, it drops off to almost nothing. By scanning the tip across the surface and using a feedback system to keep the tunneling current constant by moving the tip up and down, the microscope can map out the bumps and valleys of the surface with atomic precision. Those bumps and valleys are the individual atoms. We are literally using quantum tunneling to feel our way around the atomic landscape. We are leveraging a phenomenon that defies our common sense to create a picture of the very building blocks of matter. Even some of the most fundamental processes of nature, like radioactive decay, rely on tunneling. In certain heavy, unstable atomic nuclei, a cluster of particles, an alpha particle, is rattling around inside. It is held in the nucleus by the strong nuclear force. This force creates a potential energy barrier, like a fence around the particle. The alpha particle doesn't have enough energy to jump over the fence and escape. Classically, it should be trapped forever, but every so often the alpha particle's wave function tunnels through the barrier. It appears outside the nucleus free and flies away. This is alpha decay. The probability of this happening determines the half-life of the radioactive element. For some elements, the probability is high, and they decay quickly. For others, the barrier is wider or taller. The tunneling probability is minuscule, and their half-life can be billions of years. But the underlying mechanism is the same: a particle escaping from a prison. It didn't have the energy to leave. So, what does this all mean for our understanding of reality? It means our logic, the intuition we built up from throwing rocks and climbing hills, is a special case. It's a useful approximation that works beautifully in our middle-sized world, but it is not the fundamental law. The real laws of the universe are probabilistic, not deterministic. The universe is not a set of gears and levers. It is a haze of possibilities governed by the mathematics of waves. Quantum tunneling reveals that the universe is far stranger and more subtle than it appears. It tells us that barriers are not always absolute, that empty space is not truly empty, but a stage for the fizzing and leaking of probability waves. It suggests that the link between cause and effect might be fuzzier than we thought. It forces us to accept that a particle can be in multiple states at once, and that its properties are not fixed until we measure them. This can be a deeply uncomfortable idea. We like certainty. We like a world that makes sense. The classical world is comforting. The quantum world is not. It replaces the solid certainty of is with the shaky probability of might be. It tells us that at the most fundamental level, there are questions with no definite answers. You cannot ask how the particle tunneled in the classical sense of its journey, because the very concept of a classical journey does not apply. But there is also a kind of beauty in it. It shows that the universe operates on a logic that is grander and more creative than our own. The rigidity of classical physics would have led to a dark, cold sun. The flexibility of quantum mechanics, its willingness to allow for the improbable, is what sets our star on fire. The impossible leap that defies our common sense is the very same leap that powers life itself. In the end, quantum tunneling doesn't truly defy logic. It defies human logic. It defies our evolved macroscopic intuition. It simply follows a different, deeper logic, the logic of quantum mechanics. It's a reminder that the universe is under no obligation to make sense to us. We are the ones who must adapt our understanding, stretch our minds, and learn to accept a reality that is built not on solid certainties, but on the delicate and mysterious dance of probability. The ball can, in fact, appear on the other side of the hill. We just have to be willing to look at the world not as a collection of tiny balls, but as a symphony of invisible waves. And in that shift of perspective, the impossible becomes not only possible, but essential.